Hello, my name is Matthew Vowles, and welcome to the course on causality for social science. We're going to be talking about causal inference, directed acyclic graphs, and machine learning. Feel free to get in touch with me via my email here or via Twitter if you have questions. This first video is just to give you an overview of the course, so you can jump to the parts that are more interesting to you, but also to give you an overview of what's to come. I'll start by saying who the course is intended for. It's mainly intended for master's students, PhD candidates, and postdoctoral researchers in the domains of psychology and social science, but of course others are very welcome as well, particularly professors. Perhaps if you want to learn some different approaches to research or analysis, you're very welcome to join. The only background knowledge I expect is some kind of statistics training, the sort that you might expect of anyone who is already doing some form of applied research. You may even have some background in causality, but not in machine learning, or in machine learning and not in causality. So you're very welcome to join along if you fit those kinds of criteria. This is the course schedule. It's in 9 parts following this one. We're going to begin with a motivation for why causality is useful, talk about also what's happening in theory in psychology and social science. Part 2, we'll talk about how we can use directed acyclic graphs to help specify our theory. Part 3, we'll start talking about how we can use what we've learned from directed acyclic graphs to achieve something called causal identification. That is to say, going from a causal quantity, which might be very idealized, to a causal quantity. And that causal quantity will be valid under a number of strict assumptions, strong assumptions. We'll be using in particular the backdoor criterion for that. Part 4, we'll be talking about causal discovery. Not a long section, really just to give you an idea that it's possible in some situations. Part 5, we'll start to introduce machine learning, some of the basics, train test splitting, cross-validation, and so on. Part 6, we'll talk about machine learning for prediction, which is a task which can still be helpful for theory development. We'll talk also a bit about explanation there to try and understand what our machine learning algorithm is doing. In part 7, we'll talk about machine learning for plug-in estimation. So here we'll be bringing back the causal theme and show how we can use machine learning for causal inference tasks. In part 8, we'll talk about how we can use machine learning and still get statistical inference, that is confidence intervals, p-values, all the good stuff that comes normally with linear models. And we'll also talk about targeted learning. And the final section is on sensitivity analysis, which provides us a way to judge just how sensitive our models are to certain mistakes we may have made, particularly when it comes to the specification of the theory. Throughout, we're going to be providing code. We'll be giving both R and Python examples. Sometimes it's one or the other, depending on how much time I've had to prepare those examples. And the idea here is that, if you're familiar with R but not with Python, I'm going to go through one or the other, but the translation is actually quite straightforward. So if you've gone through the step-by-step process in one language, actually the conversion is quite straightforward into the other, so long as you have an idea of what packages might be useful for achieving that. So here's an example working through some R code, and then we have sort of also an equivalent in Python. In terms of some resources, I've put up some introductory resources here. Daggerty is a software tool that's openly available and online. It's got an online interface, I believe. I don't use it very much, but I know it's very popular, so I've included it here. There's also some background reading as to why we should start using causality in psychology to help us motivate these topics. It's quite interesting to also hear about some of the history behind causality and statistics in the last 100 or so years. In particular, this interview with Judea Pearl sort of brings to light some of those elements and some of the controversy surrounding causality in the applied domains. There's a paper of mine here, which is about how we should deal with different types of model misspecification, in particular functional misspecification, so using a linear model when it's not linear, and also structural misspecification, getting the causal structure wrong, and that actually really underpins a lot of the motivations for this particular course. Furthermore, I also have a pipeline that's supposed to help psychologists start to use these techniques as part of their research, and it's sort of a step-by-step process with associated code, and it's actually a Jupyter notebook online with annotations to help people start applying this as quickly and efficiently as possible. There's a course that I've sort of leaned on for material by Brady Neal, which is absolutely excellent. I highly recommend checking it out. It's much more general than mine in the sense that mine's more geared around social scientists and psychologists. And also there isn't a machine learning section, but nonetheless, it is an absolutely fantastic course, highly recommended it. The book Causal Inference and Statistics, a primer by Judea Pearl, Madeleine Glimore, and Nicholas Jewell is also a very accessible introduction to the use of causal techniques. So this course, I'm really bringing together three things. One is causality, the other is theory, and the other thing is machine learning. And in my view, these are all really important to consider together. Machine learning, because it helps us avoid assumptions about linearity, restrictive assumptions on parametric form, which might be affecting our ability to do valid research. Causality, because it helps us avoid issues with incorrect assumptions about the structure and underlying data generating processes. And theory is the thing that I think we really care about at the end of the day. We want to develop theories that mean something and help us manipulate and change and improve people's lives in the real world. So here, as I say, causality, tools for deriving causation from correlation and association, machine learning tools for estimating quantities with minimal assumptions about the functional parametric form, and theory, specifying a world or model process which helps us to understand natural phenomena. That brings us to the end of this first section, and I'll see you in the next part.